During the last lecture, I mentioned about how is a gimbal locking, and I checked. I googled gimbal locking and gimbal lock. So there's a Wikipedia site, and there's a nice video. So if you wanted to learn how is a gimbal locking, and now when you check the streaming and afterwards recording, then you can see how you can spell the gimbal locking. Another thing that I mentioned that there's a lot of stuff available is quaternions. This is how you spell quaternions. So rotations and quaternions. I mentioned that there's hundreds of books. Not really the case, but 177 books about quaternions, rotations. And even today you can find some scientific journal articles that explains like the new way to describe the body rotations. Not the new way other than mathematical new notation. So that's what still is a little bit of open question, because if you're using 3 parameters, you always have this singularity one way or another. And if you're using 4 parameters, then things becoming a little bit unclear, because then something like physical interpretation of parameters is not so clear anymore. I forgot to put my mic on. Okay, hopefully it's all right now. What about the YouTube officer? Can you check how is it streaming? So is it? Yeah, sorry about the beginning. But now it should be all right.
It's kind of.
So it's kind of unclear or kind of all right, or?
The sound is twice.
Twice?
Yeah.
Okay, so there was an echo. Is it better now? Hopefully it's better this time. So I think that it is all right, or?
Yeah, it's still an echo.
Still an echo.
Yeah. No, it's better.
So it's better now. I want to play safe, and I will put this off. So now there should not be any echo whatsoever. I hope so. So, but let's go back here. Now, again, the window is a little small, but if you don't mind, let's keep it this way. So what follows is that we will go and do the next step, which is a description of acceleration. So it's going to be very straightforward, and this time I'm not going to step in details to mathematics. So we'll take this equation, which is velocity. We obtained that from the previous slide, and I will differentiate that once with respect to time. All right, so it's easy. So I will get started from this component. I will get r dot dot, which is a translational acceleration. Makes sense. All right, then I have this one here that consists of actually 3 components. Out of the 3 components, one is constant. The constant one is a vector u bar, but anger and rotation matrix, those are not constant. So then I have to actually differentiate, then with respect to time. So first, when I differentiate this one here with respect to time, so I will get rotation matrix theta dot. Look at my notation. So this comes from this component here. And then I'll differentiate this guy here, and I will get theta dot dot, which is angular acceleration. All right, so my definition of my equation of acceleration consists of 3 components, and these 3 components, well, the 3 components are listed here. So let's look what we have. So we have something that makes sense. This one here is a translational acceleration, clear, easy to understand. And then I have here something that is due to the angular acceleration. So that, by the way, is related to rotation matrix E theta. And then I have here something that I need to look at I need to use a little bit of mathematical manipulation to figure it out, what that middle component, what that is about. All right? So I'm not going to explain the proof, but if you want to see the proof, go ahead and look at the lecture note. From the lecture note, you will see that rotation matrix E dot theta can be expressed as it is shown here. So it's going to be minus theta dot multiplied by original rotation matrix. All right? That comes, I understand this comes a little bit out of the blue sky. And you may feel a little bit uncomfortable that, okay, where that is actually coming from. But check the lecture notes and you can see the details. Okay? So I will take this one here and I will substitute it to that part of the equation. You still with me? Okay. Then I will get acceleration that consists, again, 3 components. And now we can see what are these 3 components. I still have this translational angular velocity. Translational velocity, excuse me, and translational acceleration. So let's take all that back. So the first component is translational acceleration. Then I have here something that is quadratically related to angular velocity. Okay, we need to take a look at the graph in a second, so then you can have a better understanding what this is about. And then we have here third component that is due to the angular acceleration. 3 components. Okay, let's take a look. Okay, so what are these components? So first one here, translational acceleration component, normal acceleration component, and then the tangential acceleration component. I will come back to this slide in a second, but this is what is interesting for us. So I have here a potato-shaped body, like shown here. This is my potato-shaped body. In my potato-shaped body, I have here body reference coordinate system. And then I'm looking at the acceleration of one single particle. This one here. And now this acceleration, that one here consists of translational acceleration due to the translation of the body reference coordinate system. That's my first component. And then there is a rotation, or there is a component that is quadratically related to angular velocity. And that one here is pointing this direction. Perpendicular direction with respect to rotation. Rotation takes place around this point. And then I have here this tangential acceleration to the angular acceleration. I'm sure that you're all familiar with these components. I'm not, this time I'm just using a little bit of different notation. Clear? I have some good news and bad news. Well, which one you would like to hear first? Bad news. Okay. Bad news is quite bad news. You know that inertia will be related to acceleration. You learned that already because I wrote this equation that r dot dot multiplied by mass, which this time will be the mass of the particle, will be equal than externally applied forces. Now when we're doing this substitution, when we're substituting this one here, there will be inertia component that is quadratically related to velocities. That's what will happen. So it will complicate the definition of inertia component. And now if you hear me like blue, 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 that's fine because your fellow student, they hear me exactly same way. You just pretend that, oh yeah, really? So there is a inertia component quadratically related to velocity. Yes, of course, when you say that, no, that all makes sense. All makes sense. Okay? Then, good news. Good news is that, many of you are familiar with something that is called Coriolis acceleration. And you're always wondering, okay, but where is a Coriolis acceleration? Well, we don't have a Coriolis acceleration. Why not? Because by the definition, the Coriolis acceleration takes place if a particle moves in rotating disk. Here's an example. Here's a particle, my body. And I'm moving here in rotating disk. So where's the rotating disk? That's Earth. Earth rotation. That's in a big picture, very big picture. I'm experiencing Coriolis acceleration. But in a very big picture. Typically, rotation of Earth is never accounted when we look in the dynamics of machines. It's not really needed. And, by the definition, so it's something, if the particle is moving in rotating disk. Okay, so let's look. So we have here this potato-shaped body. Potato-shaped body have a body reference coordinate system located in this corner. And then we have here global coordinate system where everything is, look, everything is computed with respect to this coordinate system. Okay, I can rotate this potato-shaped body along this angle if I want. I can put here revolute joint and I can spin it as much as I want. But nothing is traveling or translating with respect to rotating disk. Why not? Because we are dealing with rigid bodies. Because the body is rigid, the particle cannot move when I'm rotating this potato-shaped body. So that's what it is. Okay? Are you interested to learn a little more about the Coriolis acceleration, Coriolis effect? There is some good videos available. You know, some of them are listed here. So take a look. So they are very educational. It really gives you an idea what is a Coriolis acceleration. It's all about perspective. How is your perspective? Where is your reference system where you're measuring something? To shed a light a little bit about this matter, I don't know how this is going to work out, but I have here a YouTube video that I would like to play. Don't know if this is, maybe this was a risky business because now everything disappeared. Yeah, this is a risky business. Oh, so we're back. So let's not do that again. So you just go back home and you look at these links. You will recognize something that, you know, there's an experiment that is related to merry-go-round. You know what's merry-go-round? Okay, so those are the ones you can find in that play yard. So it's like a wheel that goes around, and then you sit in a merry-go-round. You go and you're spinning like no limit, and then you feel dizzy. So that's the idea of merry-go-round. So there is a video where there's a merry-go-round. 4 people are sitting here, and then there's a camera that is off from the merry-go-round. And when one is throwing the ball seems to go like here. And then another one is passing the ball, it seems to go like this. But when you have a camera that is standing here, when you look at how is a curve or how is a path of that object, it seems to be curved. It's all about where is your reference coordinate system. Extremely important in dynamics in many different perspectives. So take a look at that and think about it. Think about it in a way that we're always looking things from the coordinate system that is not rotating. Our reference coordinate system is standing still. All right. Okay. Any comments or questions? Is it clear? Quite clear. Okay. Are you ready to move on to something that is very, very important? By the way, there's a competition. If someone is counting correctly, like how many times I'm repeating very, very important, can get the award, special award. I don't know what that is. But that's what I'm keep on repeating. Everything is very, very important. Sometimes it's very, very, very important. Okay. But now we're going to move on to something that is generalized coordinates. Generalized coordinates are the ones that we're using to solve the responses. So now we have the definition of particle in a position, velocity, and an acceleration level. Now what we're going to do next is that we were looking from the definition of particle, what are the variables? What are the kind of the components that are changing its numerical values? And those are the ones that we're going to use, we will use as a variables to later to solve the kinematic and dynamic responses. So that's why generalized coordinates are extremely important. And heads up, they will be in class quiz related to generalized coordinates. I will ask you something in very near future. Clear? So you're awake. Okay, so let's get started from this one that we are already familiar with. So we have this equation that describes the particle position, with respect to global coordinate system. Now, here's just a one body. And we can extend this to number of bodies. But let's look at the one body first. So in this equation, what are the variables? What are the components that can change the numerical values when body is translating and rotating? So that's the kind of the problem we have to solve. Once we know those variables, then we will later use those variables to solve the responses. Okay? So let's get started from this guy. This guy consists of, this is a vector that consists of two components that are projection in a global x direction and global y direction. Can these guys change their numerical values if the body is translated? Yes, they can. So if the body goes to this direction, and let me change the color, so then this guy is changing. So if the body goes this direction, this guy is changing. Simple like that. Okay, then we will move on to this component. This is the sine and cosine theta. So theta is a theta, something that can change its numerical value. Yes, and it can change its numerical values when the body is rotating. That's when the theta will change its numerical values. Okay, so the final remaining component, vector u bar. Body is translating and rotating. What's going to happen to the components of vector u bar? Are they changing or remaining constant? Constant. So you all voting constant? Correct. So that's correct. So that's how it have to be. So it's constant component. So it remains constant. So for one body, so the generalized coordinates are translation to x direction, translation to y direction, and angle theta. And now we will build something that is extremely important. It is very, very, very important. So we will build a vector that is called generalized coordinates. You know, there's many different coordinate systems. Now we have a generalized coordinates that describe the system configuration. Meaning that if you know the generalized coordinates, you know how is body translation and rotation. And this vector will consist of this, the transpose of the vector r and angle theta. So the vector consists of three components. Now what if we have two planar bodies? How many coordinates we have to describe its configuration? 6. So if we have 10, we need 30. So that's how it goes. And that's what we're going to do in the multi-body dynamics, with always increasing the coordinates. Keep on increasing the coordinates. So if you have 5 bodies, you're going to have 15 generalized coordinates. Because so far, no discussion about constraints. Constraints, that's joints. Those will eliminate the motion possibilities. But so far, no discussion about that. Okay, clear. So now if I ask for a single body, what are the generalized coordinates? Can you answer that? Okay, good. So in case of three-dimensional case, generalized coordinates, you know, then we have a little more than. So we have vector r that consists of 3 components, and then we have theta, vector theta that includes the rotational parameters. We can have 3 of them or 4 of them, depending if we're going to, what is the way we're going to define the orientation. If we're using Euler angles, we're going to have 3 of them. So one spatial body needs 6 generalized coordinates. Clear? And okay, so these are the equations. A planar system, so a plane system consists of n bodies, needs 3 multiplied by n variables that are generalized coordinates to describe its configuration. Those are the ones we're going to later solve to find the system responses. Make sense? Kind of. Okay. All right. In three-dimensional space is 6 multiplied by n. And my question is this. So in body A, generalized coordinates are, and now we are speaking about 2-dimensional space, then the choices are rx, ry, rx, ry, theta. u bar x, u bar y, rx, ry, theta, u bar x, u bar y, theta. Only one is correct. So it's not yet online, but it will be now. Okay. So see slide. You need some time to think about this, or it's clear? You want to see the options again? I'm sure you want to see options again. So the options are here. How is the streaming, by the way? Are you looking to YouTube? You don't. Is it looking all right in the YouTube? Yeah. Okay, good. Two-dimensional case. We're speaking about two-dimensional case. Two-dimensional case. What are the variables to describe the body configuration completely? Think about this. This will affect, this in-class quiz will affect your final grade. How you're answering today will affect your final grade. Final grade will affect your life. So, no pressure. Okay, would you like to discuss with your fellow students, or you know what's the correct answer? You know what's the correct answer? So I need to keep this on because in Socrative there's only C slide. So I need to show this to you. Let me know when you're done. Then we will move on. Because there's one more important thing to discuss, which is very, very, very important thing to discuss. You're done. All of you guys entered your answer? Okay. Success rate, 60%. It's higher than that? Higher than 60 or lower than 60? 75. You say 75. Okay, so that's your lottery coupon. Anything else? 75. What was? 55. 55. So you said 55. So last time you were close. So what is your guess this time? 82. So you think we're going to score that high? We'll see. Ready? Okay. So it is moment of truth. I'm going to click this one here. Then we will see. You ready?
Yeah.
75. Yeah, so, nice. All right, I need to bring a coffee coupon to you guys. Nice. Good scoring. Good scoring. But, if we go back here.
Now I am closer. This is 79.
79.
79.
So what these could they?
My guess was 82.
82. And these guys, they say, what is that they said?
75.
Okay, so it goes to you
I
then.
am closer.
Thank you. So it's you. So it's you then. My mistake. It's complicated math and I don't have a computer with me. So I do. But I'm not using that in a proper way. Okay. So let's look at the options here. The first option makes no sense because it only describes translation. So we're missing a critical information about rotation. Third option makes no sense because we have vector u bar. Vector u bar is constant. We're looking variables. So that's why it's no good. This is absolutely no good. This is the worst option ever. Because what is that we have is two constant values and then the angle theta. Makes no sense. So this is the correct one. So this is the one that makes sense. Okay. Now, we will move on to something we need when we're carrying out the kinematic analysis. That's constraint equations. So now you know how is a single body. You know how to describe particles in position and velocity and acceleration level. But like you learned from my first lecture, the single body is not a multi-body system. So we need multiple bodies, like the title multi-body dynamics is implying. And then those multiple bodies have to be combined with constraints, joints. And now what we're going to do next is that we will look how is that we can describe these mechanical joints and how we can do that mathematically. Mathematically they are called constraints, and the constraints are limiting the motion possibilities. That's what we're going to do. So here's a concept that is important for you to understand. This is what I explained to you already. So because of the constraints, their bodies are no longer free to move as they want, but instead they have to follow the certain pattern. And the certain way comes through the constraints. And now this certain way, the systems, every single system will have a certain number of certain waves to move. And those waves will later be called as a number of degrees of freedom. But already for your information, the crankshaft mechanism shown here have 1 degree of freedom, meaning that the system can move, as an entire system can move one way only. So if I, for example, take a hold of the piston body and I force that to go to the left-hand side direction, other bodies that are connection rod and crankshaft, they have to follow the certain way. And there's only one way that they have to follow. There's no alternatives. That's where the number of degrees of freedom is coming from. And now what we're looking next is that we're looking at the mathematical definitions, how we limiting the motion possibilities. That's our goal in the rest of the day. We don't have that much time. I know that you guys are busy and you need to be off soon, but we still have a time to explain this. And I have an example that clarifies the whole deal. But now, before stepping into this example, let's look at the big picture. The big picture is this. So we have vector of generalized coordinates. You know what they are. Those are the coordinates that define the system configuration, each one of the bodies in the system. And those coordinates are defined mathematically as, shown here. There is a vector of G. So I have here a certain number of generalized coordinates. Like, for example, if I have 2 planar bodies, the vector G consists of how many components? 6 components. Okay, then I have a number of constraints, and those constraints, and I'm actually putting in a vector. It's a vector that is a function of generalized coordinates and possibly time, depending on what kind of constraints we're dealing with. And now, if you look at what's inside of this vector, I have here constraint equations that are independent constraints that are a function of generalized coordinates. So that's the concept of constraints. Clear? No, I don't trust you. So if you understood the concept of constraint equation based on this, it's not possible. It's not physically possible. So I need to explain you an example, and based on the example, maybe slowly you can get an idea. This is a big concept. This big concept tells you nothing how you can use the constraints. We will get back to this a little later. All right? So here's my example. So I have here 2 potato-shaped bodies. So I have here a body that is called body A. Here's the name. So this is a body A, and it have this shape. The body A consists of body reference coordinate system that is located here. Then I have another body. That body is called body B. Here's a body B. Body B too is a potato-shaped body like this. The body reference coordinate system is located here. I want to constrain these bodies together in such the way that there is a revolute joint located in a point O. Point O that is common for these 2 bodies. That's where I'm going to place the revolute joint. That's what I'm going to do. How can I do that mathematically? Well, I can do that mathematically such the way that I will go back to the equation that I'm very much familiar with. So I'm going to use this equation that you know back and forth already, and I'm going to define this point O using this equation with respect to body A, and I will do the same with respect to body B. And once I put those to be equal, what that means? It means that these points have to be common no matter what, because of the constraint is forcing that point to be common. That's the trick that I'm using to introduce a revolute joint. Clear. Big picture is clear. Okay, what it means in practice. So it means in practice that I define the point O. Look at this particular point that I'm defining with respect to body A, and I'm defining the very same point using the body B. This one here. So the idea, let me describe the idea one more time here. So I'm aiming to describe this point here, and I'm traveling to this point using two different ways. My first way will be via body A, like this. My second way will be via body B, like this. And then I'm simply putting those two definitions or two ways to be equal, meaning that point O will be combining these bodies together. And then these two bodies are no longer free to move as they want, but instead they have to follow the constraints, and then they can move relatively with respect to each other like this. They can travel together like this. They can travel to y direction like this, and they can rotate together like this. But they cannot separate like this any longer. That's not possible, because you have to obey the constraints. You cannot violate against the constraints. Clear? Yes, we're all going to do it like this. Okay, then let's do it. Let's define the point and the way it goes. So first we're going to move to origin of the body reference coordinate system. I think it is better to change the color to green. So first we're going to move here, and I need a later figure. So we move here. So this one here is describing the translation. Then I'm accounting the orientation with help of 2x2 rotation matrix. And then with help of vector U-bar, and finally traveling to my destination, which is my final destination is point O. Okay? So that's my first way to go there. My second way is that I will get started again from the origin of the global coordinate system. I will move on to origin of the body reference coordinate system. I will account the orientation, and then my final destination I will go here with the help of vector U-bar in respect to body reference B. Okay, so then I will simply, look how these components look like. So this is my body A, this is my body B. And now when I do all this mathematical operation, I end up to have two constraint equations. Two constraint equations that I have to obey no matter what. Okay, how that sounds?
Okay.
Sounds okay. Good. Okay, and then another concept that I would like to explain to you today is the number of degrees of freedom. Number of degrees of freedom depends on what's the number of generalized coordinates, what's the number of independent constraints. So you already know what are the generalized coordinates. So those are the ones that depends on the number of bodies. What are the number of constraint equation? That depends how many constraints you have. What are the different joints you have in your system? But let's look at like this example we were dealing in the previous example. So where there was a body A, body B, and they were combined together via revolute joint here. So two bodies. How many generalized coordinates I need to describe the system? 6. What are the number of constraints because of the revolute joint? You learned that from the previous slide. How many constraint equations you need? 2. So the number of degrees of freedom is 4. Simple like this. So that's how you can calculate the number of different ways that the system can move. Then there's a special cases, there is possible that the number of degrees of freedom is equal to 0. And then we're speaking about kinematically driven system. But that's something we will get back next week. Okay, no, actually there is, shortly because I did not remember that the next slide is about kinematically driven and dynamically driven. So let me explain this concept to you. And then soon we're going to close for today. So I have here this crankshaft mechanism. And we concluded that the crankshaft mechanism consists of 1 degree of freedom. But we did not count it. So let's count it. So in a crankshaft mechanism, I have 1, 2, 3 moving bodies. All right? So how many generalized coordinates I need to describe? 9. So it's going to be 9. Then I have here revolute joints that are 1, 2, 3 revolute joints. Each one of the revolute joints, they need 2 constraint equations. So I have here 6 constraints because of the revolute joints. And then I have here 1 translational joint. You don't really know how many constraints are needed, but I will tell you. 2. 2 are needed to describe translational constraints. So 6 plus 2, that's 8. So the number of degrees of freedom is 1. Okay? Now what I do in this scenario that is shown here, which is called kinematically driven mechanism, I will eliminate the last remaining degrees of freedom. And the way I will eliminate that is that I will introduce additional constraint. Additional constraint is something that is called driven constraint. I'm saying that the crankshaft have to follow the angle that is pre-described here. So I'm saying no matter what you're doing, you have to follow this pre-described path, which is mathematically shown like angle theta have to be something. That is constraint, because it have to obey that. What happens? So then I have here 1 extra constraints and system have 0 degrees of freedom. It still moves because I have this motion inputs to the constraints, but this is something that I can solve the response by using kinematic analysis only. So I can only use the kinematics. No force is needed to solve the response, and that's what we're going to learn next week, how you can conduct the kinematic analysis. So if the number of degrees of freedom is 0 and you have these driven constraints, then it's a kinematically driven system. And you can solve the response by using just constraints, nothing else, just constraints. What if I keep the 1 degree of freedom open as it originally is, and then I'm introducing here a moment, or force, or now this time is a moment. How can I solve the response in that particular case? Well, the only way to make that happen is that I have to write the equation of motion, and I have to solve the equation of motion in forward of time. So those are the completely different concepts. So one is based on the motion, one is based on the forces. You got it? Or would you like to have a little bit of further explanations? Okay, let's think about the box. Box is in this surface, and I'm saying that this box that have to stay in a surface, meaning that this box originally have 3 generalized coordinates. And now because of the 1 revolute joint, translational joint, it's going to be 2 constraint equations, so 1 degrees of freedom. What's this 1 degrees of freedom? It's the degrees of freedom that the box can go back and forth top of this surface. That's what it is. And now I'm saying that actually you're no longer free to move as you want. But I'm coming here with the pre-described motion, and I'm saying that this coordinate here have to be like sine time. Then it goes back and forth according to this sine equation. What is that? Constraint is another constraint. How many constraint? What's the number of degrees of freedom then? It's going to be equal to 0. So all the responses is pre-described. So I can solve the system without knowing anything about the forces. Okay, that's the first scenario. That's called kinematically driven. And for a fact, I will ask this in written exam. It will happen. Okay, then I have another scenario. I will take this pre-described motion away, and I'm saying actually I have here a force that is pushing forward this box. How it will move? Well, the only way that I can find how it moves, it will be based on the equation of motion. this one here that you're already very much familiar with. Now maybe I should better write it like r dot dot, like this. Now with this equation, I can first of all, I can solve that r dot dot is equal to f divided by m. And then from this I can integrate r dot, and I can integrate r to find the response. But that requires that I have to have an equation of motion. So it's a different concept, completely different concept. So do you know what's, now do you have a remote idea what's a dynamic system? A kinematic system? Or a constraint system is something that there is too many constraints and motion is not possible. Example would be this one here with one extra revolute joint that is connecting that to ground. Motion is no longer possible. The revolute joint is here. It's locked. Okay. Makes sense. Or none of this stuff makes any sense. Starting from the particles, makes sense, kind of. Constraints, kind of. Okay. So what do you say? Should be closed for today. Any questions or comments? Now would be a good time to raise a hand and say, Aki, you know what? I don't understand. Now you can do it. But of course you all understand. This is clear. Makes sense. Makes sense. Okay, so I have a little bit of a, something that I would like you to know. This is, we will get back to this next week. So next week, if I look at something that, this is a time, this is a level of difficulty. Level of difficulty, like how difficult are the concepts that I'm explaining. LD. So we here, this is the first lecture. Now it's the second lecture, third, and so on. So we here like medium. Next week is going to be a little bit of peak. Not much. Still going to be moderate. But when we're coming to equation of motion, we go high up here. And then we come back here. So make sure you're following. Because if you're missing this, you will be very confused. Okay. See you on Monday then. And don't forget, the guided tutorials will be on starting Wednesday morning at 8:15. And I believe that those lecture rooms are located in the Studion Union building. All right, guys, take it easy. And remember to read. Read the lecture notes.